This looks like a lunchbox, but it's actually a petaflop AI supercomputer that fits on your desk. This is NVIDIA's DGX Spark, a good cube that costs $3,999, about the price of a Mac Studio, if not less expensive, yet delivers performance that used to live inside massive data centers. But hold on, how did we even get there? In this video, we'll see how did one company end up controlling the backbone of modern AI, and why are the biggest players on the planet suddenly trying to break free. This is the untold story of AI custom chip war. And by the way, you're watching Switch now. Here we break down how real technology is reshaping startups, infrastructure, and the future in minutes, not hours. If you enjoy a simple explanation of complex tech, subscribe to the channel and stay with us. Let's dive in. Let's start with the company that still sits at the center of everything, NVIDIA. Before anyone could escape GPUs, NVIDIA made them smaller, faster, and personal. You see, compared to a CPU which focuses on a few powerful cores optimized for sequential logic and control, a GPU is built to run thousands of operations in parallel. That makes GPUs perfect for graphics, gaming, and 3D rendering, and turns out even better for machine learning and AI workloads. NVIDIA built its entire empire on this idea and grew into a multi-trillion-dollar company. Today, AI literally runs on NVIDIA. We've already made a two-part series breaking down NVIDIA's dominance from GPU infrastructure and Kubernetes to its massive investment across the AI startup ecosystem. But this gold cube is quite special. With 128 GB unified memory, Spark can run 200 billion parameter models locally. It's a fully self-contained, developer-friendly machine running NVIDIA's full AI software stack. No cloud GPUs required. Under the hood is NVIDIA's Grace Blackwell superchip, the same engine driving trillion-dollar data centers, now shocked into a box that weighs just 2.6 pounds. This one even hand-delivered the first unit to Elon Musk, just like he did with the original DGX system he gave Sam Altman at OpenAI back in 2016. We wouldn't be surprised if one day we had an AI supercomputer the size of an iPhone, or even smaller like a ring or other functional wearable device. Well, the human being is certainly not one of them. But first, what exactly is an AI supercomputer? An AI supercomputer is a system designed to train and run massive AI models by coordinating thousands of GPUs or custom accelerators, all working together in parallel. An AI data center is the physical engine behind it. Specialized hardware, dense power delivery, advanced cooling, high-speed storage, and ultra-fast networking, all built to keep AI training and inference running continuously at scale. If you want a deeper dive into how AI supercomputers actually work, check out this video on our channel. Now that you know what an AI supercomputer really is, here's the next mistake most people make. They assume all AI workloads scale the same way. Well, they don't. Training and inference are completely different stories, and no company has learned that lesson more than Meta. You see, 20 years ago, Meta ran a simple LAMP stack. A handful of servers, a few thousand users. Today, it operates a globally distributed system serving 3.4 billion users. First, it scales software, databases, caches, the social graph, then hardware, custom data centers, private fiber, and HPOPs across the world. But here's the kicker: in the age of AI, that playbook is obsolete. By 2022, large language models push training from hundreds of GPUs to tens of thousands. Meta learned fast. AI training is like web traffic. There are no retries, just raw infrastructure limits. By 2023, they had built two 24,000 GPU clusters and had emptied 5 production data centers to create a 129,000 GPU supercluster for NAMO-class AI models. But the raw scale wasn't enough. Meta is now building Prometheus, a 1 gigawatt AI cluster spanning multiple buildings and connected by long-distance training networks. They're mixing NVIDIA, AMD, and custom TIA silicon, investing in advanced cooling, memory disaggregation, and silicon photonics. Training big AI models is easy for them now, but infrastructure that doesn't break, that's a real challenge. Meta proved something critical. At a certain scale, GPUs stop being a solution and start becoming incredibly expensive, even for tech giants. That's when the focus shifts to cost-cutting, layoffs, internal pressure, and hard trade-offs. Past the AI story we're only beginning to see. When that happens, every AI company faces the same choice. A. Keep buying more GPUs. B. Build their own custom AI chips. And this is where the real chip war begins. OpenAI realized the future wasn't just about building better AI models. So instead of waiting on NVIDIA, they made a radical decision. OpenAI had teamed up with Broadcom to build its own custom AI chip, a project powered by a massive $10 billion investment aiming for mass production by 2026. And yes, it's all part of a plan to finally break free from NVIDIA's GPU monopoly. They even give it a really cool code name, OpenAI XPU. Good job, OpenAI. But here's the kicker, this isn't a general-purpose GPU. It's a chip co-designed around OpenAI's own model architectures, kernels, and training patterns optimized for training parameter model training, the kind of customization NVIDIA simply won't build for a single customer. The magic comes from Broadcom's XPU platform, which enables OpenAI to plug in its own IP while utilizing Broadcom's licensed interconnect fabrics, memory controllers, and SerDes IP, thereby avoiding the pattern minefield that often kills most custom silicon projects. Behind the scenes, these Google GPU engineers are rebuilding OpenAI's entire training pipeline to run tens of thousands of these accelerators. If you think this is a brilliant idea, Google's already a decade ahead. You see, while NVIDIA controls up to 92% of all AI accelerators on the planet, Google built its own escape plan. TPUs, or Tensor Processing Units, co-designed with Broadcom, manufactured by TSMC, and optimized exclusively for AI, no gaming, no graphics rendering, just raw model training. It all started in 2014 with one terrifying question. What if our 2+ billion Google users talk to Google Assistant for just 30 seconds a day? Google calculated they would need to double their global data centers, or cleverly build a chip 100 times more efficient than general-purpose hardware at the time. Fast forward to today, 6 generations later, TPUs run YouTube ads, process videos, and even power Pixel phones. Google translated all its major AI models on them, Gemma 2, Imagen 3, and now Gemini 3, which were trained on TPU V5e and V6e pods. The result, Gemini 3 delivers 1.7 times stronger reasoning and 2 times better factual accuracy than GPT 5.1. Even Sam Altman is starting to get nervous about Google's accelerating AI momentum. Amazon carefully watched Google, then went one step further. What happens when the world's biggest cloud provider builds massive AI data centers without a single NVIDIA chip inside? Yeah, Amazon put a Google TPU, and Microsoft migrate moved quietly, stepping off the GPU battlefield to build their own AI chip. In the middle of Indiana, what used to be farmland is now a 1,200-acre, $11 billion AI complex called Project Rainier, already training AI frontier models and powered entirely by Amazon's custom chip Trainium 2. The story doesn't stop there, though. At reInvent 2025, Amazon unveiled 23 Ultra Server, a 3nm monster paired with the Graviton 5 CPUs. Each server packs 144 Trainium chips, and thousands of these servers can be linked into clusters of up to 1 million chips. It's 4 times faster, 4 times the memory, and 40% more energy efficient than before, cutting training and inference costs for Anthropic, Carol Curry, Splash Music, and more. And here's a twist no one saw coming. Amazon is working on Trainium 4. It will support NVIDIA's NVLink Fusion, letting Trainium and NVIDIA GPUs operate in the same high-speed fabric. Even AI apps built for CUDA can run on Amazon Silicon too. So now, the question isn't whether Amazon can catch NVIDIA. I'm curious about what happens when they finally start working together. Microsoft tried to do the same and learned how hard custom silicon really is. So instead of going alone, they made a strategic move, co-designing the future of AI hardware with OpenAI. Back in 2024, Microsoft unveiled Maya 100, its first custom AI accelerator purpose-built for cloud-scale workloads inside Microsoft Azure. Maya 100 is an 820 square millimeter chip built on TSMC 5nm process, paired with with the 4 HBM stacks delivering 1.8 TB per second of memory bandwidth. Maya scales to ultra-fast Ether speeds of up to 4.8 TB per second with built-in encryption for confidential AI workloads. But here's a reality check. Building an efficient AI silicon is hard, and software matters just as much as hardware. So, Microsoft quietly pushed Maya 200 to 2026. Now it's leveraging OpenAI's custom AI chip designs with Broadcom and extending them across Azure. Well, if only it were that simple. OpenAI didn't just build chips. Even shopping, they struck a massive deal with Amazon, bringing custom AI models into Amazon's products in exchange for $50 billion investment. To Microsoft though, they didn't say this one out. They released Maya 200 at the beginning of 2026, which claimed to be the most efficient inferencing system Microsoft has ever deployed, delivering about 30% better performance per dollar. We get it. In the AI race, saving money is almost as important as burning it. It may look like a setback, but it's the next phase of the AI infrastructure war, where the future is not a single vendor silicon. It's co-designed AI systems, models, chips, and networks built together. But not everyone wants custom chips. Some want raw power. Elon Musk chose the most aggressive path possible: buy everything, build immediately, and deal with consequences later. Sounds very Elon Musk, doesn't it? What if I told you the most powerful AI supercomputer in the world isn't in Silicon Valley, but in a small town called Memphis in Tennessee, and is making headlines for the wrong reasons? Inside an abandoned factory, Elon Musk XAI built Classes, a data center monster packed with over 100,000 NVIDIA H100 GPUs, assembled in just 90 days. To train his next-gen AI, Grok, each GPU delivers 4 petaflops of compute. It's more processing power than small nations like Finland or Estonia. To feed that kind of power, XAI pulls 150 megawatts from the grid and fires up 35 gas turbines, generating 420 more. As a twist, Logo says this supercomputer is just training AI models exploding their air. But this isn't Musk's first game on AI infrastructure. Back in 2019, Tesla's Dojo promised to beat NVIDIA with custom D1 chips, a supercomputer built for self-driving and robotics AI that could add $500 billion to Tesla's value, until it collapsed under its own ambition. Now, with Classes, Musk is betting big again, not on cleaner tech, but on raw AI power. The question is, will this time finally work? And just when it feels like we've reached the limit of classical AI infrastructure, NVIDIA opens an entirely new front. AI and quantum computing run together at a microsecond latency. In Japan, based ABCIQ supercomputer just went live, a 300,000 square foot powerhouse built by 2020 NVIDIA H100 GPUs and Quantum 2 Infinite Band, merging AI and quantum processors into a single hybrid platform that's redefining research from drug design to climate modeling. Meanwhile, in Taiwan, ASUS and NHC are building an AI supercomputer with 1,700 H200 GPUs and Blackwell Ultra chips designed for sovereign AI, quantum simulations, and models that understand local languages and culture. And now in Germany, the Unix Supercomputing Center has deployed the first NVIDIA GTX quantum system, linking Grace Hopper superchips with quantum controllers to achieve 4 microseconds latency. That's 1,000 times faster than before. Want to see how quantum computing actually works? This video is already on the channel. Regardless of GPUs, TPUs, QPUs, or any other AI accelerator, the goal has always been the same: process more data faster, cheaper, and more efficiently. Every new chip, every new architecture, every new data center design is just a different adaptation to solve that problem. At one end, we have massive data centers powering enterprises. At the other, we need a smaller, powerful computing for consumers. And that's where the future of AI infrastructure is heading. Here's the big takeaway. AI progress isn't limited by ideas or models anymore. The companies that win the AI race won't just have the smartest models, they'll have the best AI systems, deeply integrated across a broad set of products and platforms. If you enjoyed this breakdown, you may be interested in other videos in this AI infrastructure playlist. Subscribe to our channel and our newsletter if you're interested. I'll see you in the next one. Hi Techies! If you're interested in passing Kubernetes certifications or any certification for the Linux Foundation, there's a whole new world waiting for you. Go to the Linux Foundation catalog and grab it. Use code Cloud Modem to get 30% off. And guess what? It works for bonus too. 30% off for all certifications all year round. Because the best way to predict the future is to invent it. Now it's your turn to make it happen.